Hello. The purpose of this video is going to be to walk you through the active calculus problems 1.3.3 and 1.3.4. Okay, so the first problem is the water balloon problem. A water balloon is tossed vertically in the air from a window. The balloon's height in feet at time t in seconds after being launched, given by S of t, is equal to negative 16t squared plus 16t plus 32. We want to use this function to respond to each of the following questions. Sketch an accurate labeled graph of S on the axis provided in figure 1.3.1. You should be able to do this without using computing technology. Now, when they say you should be able to do this without using computing technology, they think that you can figure out the y-intercept, the minimum, and then the x-intercept. But we don't have to do that. We're going to use Desmos. So I'm going to go ahead and open up Desmos. All right, and I'm going to type in 16t squared plus 16t plus 32. And I'm going to zoom out so we can see the appropriate. Oh wait, it's not going to do this unless I define it. I gotta zoom out, and I'm gonna zoom in around the y-intercept and the maximum. So what I'm going to do is I'm going to go ahead and I'm going to make this a table because I'm going to need to figure out some stuff. So I'm going to open this up. So I sketch the graph. I want to compute the average rate of change on the time interval 1 to 2, include my units, and write one sentence to explain the meaning of the value that I found. So I'm going to go back to Desmos. And I'm going to figure out what 2 and 1 are. And I'm going to do 0 minus 32 divided by 2 minus 1. And that gives me a negative 32. So that means that I am falling at between 1 and 2 seconds. I am falling at negative 32 feet per second. Okay. And that's what the sentence they want. Now, this part is a lot of work. C is a lot of work. It says use the limit definition to compute the instantaneous rate of change of S with respect to time t at instant a equals 1. Show your work using proper notation, include units on your answer, and write one sentence to explain the meaning of the value you found. So that is a heavy question. So I've already done this out, but I'm going to take you through this math again. If you are confident in this algebra, you can tune out, but I'm gonna go ahead and go through it. So the limit of h approaches 0 of negative 16 times a plus h. This is the difference quotient, not the difference quotient, but the limit definition. Minus 16a plus h plus 32 minus 16a squared plus 16a plus 32 all over h. Now we want to figure out what happens when a equals 1. So that becomes the limit as h approaches 0 of negative 16 1 plus h squared plus 16a plus h plus 32 minus, I'm going to drop the parentheses, so this becomes plus 16a 1 squared and that's a 1. So this is 16 times 1 squared minus 16 times 1 minus 32 all over h. Now again, this is going to be really helpful to you if you remember 1 plus h squared or a plus h squared. So a plus h squared is always going to be a squared plus 2ah plus h squared. Okay, I distributed that out and I got a and I get that. So this allows me to say limit as h approaches 0 of negative 16 times 1 squared plus 2h plus h squared plus 16 times 1 plus h plus 32 plus 16 minus 32 all over h. We've got the limit as h approaches 0 of negative 16 minus 32h minus 16h squared plus 16 plus 16h plus 32 minus 16 minus 16 minus 32 all over h. We're still going with the limit as h approaches 0. We're not done with that yet. We just need to cancel stuff out now. The minus 16 and the plus 16 cancel out. The plus 32 and the minus 32 cancel out. One of these should be a plus 16. Because I should only have 1 16 left. So 16 plus... minus plus 16a squared. Yeah, but that becomes a minus again. No, it's a plus. This is a plus, so this is a plus, so these go away. So that leaves me with the limit of negative 32h minus 16h squared plus 16h all over h. So the limit as h approaches 0 of h times negative 32 minus 16h plus 16 all over h. Cancel out the h's. Limit as h approaches 0 of negative 32 minus 16h plus 16 equals just minus 32. This goes to 0 plus 16. That equals a negative 16 feet per second. So at that instance, at 1, we are going at negative 16 feet per second. Okay? So that's the limit definition. That was a really heavy problem. On your graph, sketch 2 lines, one whose slope represents the average rate of change of s on 1 to 2, and the other whose slope represents the instantaneous range of s at instantaneous a equals 1. Label each line clearly, so we'll go to Desmos and we'll get a screenshot of that. I'm going to export an image. Medium, thick. Download my ping. Open. Will you let me copy it? Share. Copy file. Let's put it right in here so that we can draw these lines. Come on. So this is at the instantaneous rate at y equals 1. So I'm going to get a ruler out, and I'm going to just try and draw a line tangent to that to the best of my ability. Okay. And then between 1 and 2, I can't really draw that. 2 goes all the way down to 0. So it's going to have a steep line like that. So this is my tangent line. This is my secant line. This line represents my average rate of change. And the tangent line is my instantaneous rate of change. Okay. So that's what that question's asking for. Now the question is, for what values do you expect S of A to be positive? Why? Answers the same questions when positives are replaced by negative and 0. So I'm going to go back to Desmos, and I'm going to tell you that when your derivative is positive, your graph is increasing. So between 0 and 1, or 0 and 0.5, we are increasing. So between 0 and 0.5, we are increasing. Okay. And then, let's see. When you are negative, you are going to be decreasing. So we are negative between 0.5 and 2. I'm just trying to show you that because we get to 0.5 and 2. We don't worry about what's going on beyond 2 because we can't have a negative height with the water balloon. The water balloon is broken at 2. So, between 0.5 and 2, we are decreasing. When we are at 0, we are at 0.5. So f prime of 0.5 equals 0 because we are right here. We have a slope of 0 there in our tangent line. Okay, so that's that problem. I will not be covering the population problem in this video because I am almost 15 minutes in. Stay tuned later on this week for the population problem.